Good evening, everyone. Welcome to our Fire Ecology of Oregon webinar series. We're very pleased to have you all here with us tonight. I want to just briefly acknowledge the other folks who are here to help answer questions tonight. I'm John Punches. I'm the Extension Forester in Northeastern Oregon. I'm joined by Micah Schmidt, who is the Extension Regional Fire Specialist in Northeastern Oregon. We're joined by Jacob Putney, who is the Extension Forester in Grant and Baker counties, by Carrie Berger, who is with the Extension Fire Program, and with Andrew Merschel, who is going to be one of our speakers later on, has been a great contributor to our knowledge about fire ecology. So we're really pleased to have this group here. Our presenter tonight is Ariel Cowan. She's the Extension Regional Fire Specialist in Central and South Central Oregon. Ari, welcome. We're grateful for being here. Ari's going to talk to us about fire ecology and soil. I had originally kind of put in the materials there, fire ecology in forest and rangeland soils, and Ari kind of corrected me and said, hey, I really only agree to talk about forest soils. So we're going to let her hold to that more kind of specific thing there tonight. So we're just grateful that she can be here to share this. It's such a huge field of study that really we would need an entire series just to talk about ecology and soils. So Ari's got a huge job to kind of pare it down. So we know there will be questions, and just so you know in advance, there are probably going to be questions that we don't get to, but we're going to keep track of those, and we'll reach out to our peers at OSU to try to make those connections and get those posted back to the website so we can all benefit from that. So with that, just let me remind you that if you have a question for Ari as she goes through her material, something directly related to her presentation, please ask that question through the Q&A box in Zoom. So not the chat box, but the Q&A box. So something directly related to what Ari is presenting there. We don't have the luxury of answering questions in real time in this format. There's just like too many of you and not enough of us. So Ari will stop periodically and we'll catch up on those questions. So please use the Q&A function for that thing. If you have general comments, please keep them nice, but feel to put those in the chat box or anything that has to do with a technical issue, like with your connection or something like that. Please drop that into the chat and one of us will take care of that. Jake, could you remind us how we do continuing education credits in these courses?
Yeah, John. So this series is approved for continuing education credits for the Society of American Foresters, Associated Oregon Loggers, and the Oregon Certified Burn Manager Program. For SAF, there is a form on the series website. If you download that form and fill out your name, contact information, and SAF number, as well as the keyword that I'll announce at the end of tonight's session, I can get those credits recorded. And you can either return that form after the session this evening, or if you want, you can wait until the end of the series and return just one form. For Oregon Professional Logger credits, if you just send me an email with your name and the company you're representing, I can get those recorded. And same with Certified Bird Manager. If you just send me an email after tonight's session, I'll record those as well.
Great. Thank you, Jake. And with that, I'm going to turn it over to Ari and let her bring us up to date on fire ecology and soil. Thank you, Ari.
Thank you, John. Good evening, everyone. I'm excited to talk to you this evening about fire ecology and soil. I just want to start by introducing myself. I'm a regional fire specialist for OSU Extension. I cover, it says on there, Central and South Central region. From north to south, that includes the Confederate tribes of Warm Springs, Jefferson, Crook, Deschutes, Klamath, and Lake counties. I work on connecting partners on topics like fire outreach and education, fire ecology, prescribed fire use, wildfire preparedness, and more, with the goal of empowering communities to build resilience to wildfire and hone fire for its uses. So my background before entering this work was a mycorrhizal ecologist. Maybe some of you will be familiar with that term. I'll say a little more about what that means later. So I studied the soil fungi that partner with trees, which led to my research on how fire impacts those important networks. So this is my opportunity to nerd out with all of you on some of my passions, soil ecology and fire ecology. So I just want to start by saying that there is so much to learn on this topic, much more than this webinar can cover. So for the most part, I will be staying very high level and summarizing fire ecology and soils. But I really recommend looking at like the links that John had mentioned there on the website. We're going to put some more links up there after this presentation. And I also recommend checking out the research coming out of the labs of Jeff Hatton and Kevin Bladen and others from Oregon State University. Not to mention that also the Dean of the College of Forestry, Tom DeLuca, is an expert on fire effects on soils. So honestly, if there are any questions that we can't answer for you today, we might direct them to those researchers and their students, but we will do our best because this is a pretty exciting topic and there's just so much to learn about it. So I really appreciate from the last two webinars from the series, I appreciate the background that John Punches and Micah Schmidt gave to the basics of fire ecology and fire regimes. And we've heard in those webinars about historical fire and how conditions have changed fire regimes today and the impacts to different ecosystems, such as through increased fuel density. It was also mentioned the fact that we were experiencing hotter, drier, and longer fire seasons across Oregon and much of the West. So if these conditions are drying out dead and living vegetation, what are they doing to the medium that plants grow within? What are they doing to the soils? So for an overview for this presentation, I'm going to be just going over first, what are soils? Talking a little bit about forest health or no, soil health. We talk about forest health too. We'll go into soil health, and then soil ecosystems impacts from fire, some of the benefits they get from fire, and where do we go from here? So I just want to start out by asking if everyone can put into the chat some of your answers that you may have to this question. What are some of the ways that fire interacts with an ecosystem, much like the one that you see in this grainy picture of a forest? What are some of the ways that fire interacts with an ecosystem? How might it affect the trees or other aspects of this forest in this picture? Just put one or a few words. Oh yeah, here we go. Alters species composition, kills microbial life, clears underbrush, and introduces nutrients, opens canopy. Yeah, we're going to get a little into soil chemistry. Scatters seeds underground. Yeah. Nutrient cycling, stand replacement. So really fantastic. I appreciate it. You can keep going with some of those answers. And I would say that often when I ask a question like this, I think one of our first inclinations is to think of what happens to the above ground, what happens to these trees or what happens to wildlife. That's often a focus. But what I don't hear all too often is how it affects below ground, how it affects the soil. And so actually I had done this Wordle, this like fun activity where you can take all of the words from, in this example, it was from research papers on soil effects, fire effects on soil. And the larger word is the one that's repeated more often in that piece of text. And so from this Wordle, you can really see some of the words that stand out. And it just really goes to show, okay, in a lot of those studies on fire effects on soil, there's a lot of focus on biota, the life in the soil, the moisture in the soil, the roots, the pH, the nutrients, and soil erosion. And I saw in the chat, some of you had referred to some of these effects on soil. So it's great. Some of you are already thinking about soil. So what is soil? So in a nutshell, soil is a natural body comprised of solids, minerals and organic matter, liquid and gases that occurs on the land surface of the earth. Or potentially other places, but this is the definition for here. And that if you look at this, what, the percentages of what makes up soils, roughly air 25%, water 25%, 45% minerals. And then I really want to focus on that 5% of organic matter. This sounds small, but it's a very crucial component of soil. And here we see the breakdown even further of 10% being organisms, 10% being roots, and 80% humus, which is some of that more decomposed and actually more stable form of organic matter that's beneath the duff of the soil, but still at the soil surface. We'll get a little bit more into that in a bit. So soil orders are ways that soils have been classified. There's 12 different orders of soil, and these are them, and they basically are classified by their component of texture, which would be their proportion of sand, silt, and clay, their depth, the depth of that soil, the temperatures they experience, the amount of organic matter, the quality, the type of organic matter that's in them, their parent material. Parent material referring to like, okay, well, what rock helped to produce some of that soil? All of this influenced by the topography, the weather, where that soil is, and the weathering of that soil, the act of how that soil has been broken down and created, basically the genesis of that soil. And then also what else describes these soil orders is also the ecosystem that grows from it and in it. So here we see these 12 orders, some of them being, for example, mollisols, soft, dark, semi-arid, moist, often found in grasslands. Spotozoals, often we see these in coniferous forest. And then around where I live in Central Oregon, there are a lot of andisols or volcanic soils that are well draining and don't hold moisture quite as well. So there are 12 here, but there are actually only 10 in the state of Oregon. If anyone was wanting to put in the chat, which of the two that you see here do we not have in Oregon? There's 2 of these. Any guesses? Think about some of the description here. Yeah, well, I think we have a very educated crowd here. We've got oxasoils and gelisols do not exist in Oregon because gelisols, as you see here, it's more about permafrost, very cold permafrost, that's further north. And oxasols, that's, as you see here in the description, more tropical soils. Yeah. So here now we can see in the state of Oregon where you can find a lot of those 10 different soil orders. So it's really neat how you can see the Cascade Mountains really stand out, and there are a lot of andisols. Makes sense. They're volcanic soils. But there really is quite a mix of all these different types of soils that we have all throughout Oregon. And it matches really well. I just want to point, it matches really well with the plant ecosystems that we find existing in those places. So it's like the soils are affected by the plants that live there, but the plants live there because they're able to grow in those types of soils. So I want to zoom in on an example. And I don't know if any of you have been able to use this really fantastic tool called Soil Web. So if you just type into your browser Soil Web, you can find this great tool where you can type in any address. You can type in the address of your home and it'll go straight to it. And if a soil survey has been done there, then and a lot of these soil surveys through the USGS, they will be listed through these maps, and you can zoom in, and here we have all these different numbers and letterings, and if you click on it, you would be able to see, oh, okay, there's these types of soils, and usually it'll give you a breakdown of the percentage. For example, around here, and I wonder if anybody recognizes where I zoomed into. This is pretty distinctive. But this is in my region, and I don't know if I can use the pointer. Here we go. Nope, that's the pen. Let's use the laser pointer. So here we got, this is Black Butte, outside of Sisters, Oregon. So I want to show this as an example because it's pretty neat how soils tells a story of the geologic history of a region. And so on those cool maps, if you zoom in here, I clicked on Glaze Meadow, which is near just south of Black Butte. Then it'll just tell you on the side the different types of soils, what percent of those soils, and then you can click on them and find out even more information like the pH levels and the depths of the soil and what could potentially grow there, things like that. And why am I going so deep into this? Well, as I was saying earlier, there's different orders of soil that influence the type of plant communities that live there, and they tell a story of the geologic history of this place. What's pretty neat about this location is through the soils, it's been identified that this area used to have a river and a shallow lake going through it. And when Black Butte had erupted, had come out of, it's a cinder cone, that it actually had plugged where the Metolius River used to flow through, and forced that river below ground, that now on the other side of Black Butte, that's where there is a spring where there are the headwaters of that river. But we may not have ever known that if it weren't for looking deeper into the soils around this region. And also really interesting that we're able to identify types of soils that indicate that there were glaciers in this region, that there was a lot of sedimentation and weathering from those glaciers. So it's not just volcanic soils, but also glaciated soils. Pretty neat. Another really important influence to soils throughout Oregon would be Mount Mazama. So Mount Mazama, also known as Crater Lake. Mount Mazama used to be 12,000 feet in elevation, but around 7,000 to 8,000 years ago, the summit collapsed, and it collapsed by about a mile in depth, or somewhere around over 5,000 feet. And when that mountain erupted, it put out such an ash plume that covered the entire Pacific Northwest. I mean, some of it even made it to the middle of Montana and parts of Nevada. So really fascinating how that ash had a huge influence on the soils throughout our entire state. And the ash that was the deepest was, of course, closest to and just northeast of where Mazama was. And so that's really important to then think about not only the depth of those soils, but what they're made of, that they're often comprised of pumice, which once again, it doesn't hold water as well. And it's well filtered, and it also has a lot of ash. And the ash also had a large component of different minerals. that were beneficial to some of the plants that now grow out of it. So I just want to give a little nod to rangelands because we had mentioned, okay, well, thinking about not just forests, but also rangelands. Those types of soils are known to be very fragile. These places, say, further east of the Cascades, those are arid lands. There's not a lot of shade. And if you think about how much vegetation is growing out there, there's not a lot of organic material. So those are really shallow soils. And so because of that, when they do burn, that they end up being impacted greatly, and it takes a lot longer to replace or to restore what that soil was like before. So besides talking about soil orders and what differentiates them, we also want to think about the different layers of soil. So we have our top layer, or O horizon. That's where leaves and pine needles and plant debris will collect, and it'll be broken down. And beneath it, then there will be topsoil and the other horizons below that, till you get all the way down to the rock or parent material of that soil. And from the example that I shown before of really dry, arid soils, like in the region that I live, they can be deep, but they can still they're incredibly insulating. They have this natural insulating capability where if you were to take a temperature probe, even now in the depth of winter, that they maintain a pretty stable temperature just a couple of inches down. And the same thing in the summer, that if you were to dig down into the soil, you would find that it's a lot cooler. And so that ends up being a place of refuge for a lot of creatures, a lot of organisms. And that's certainly something to think about in terms of changing climates, that the soil can be a refuge for a lot of those creatures. So thinking about the depth of the soil, the different layers, and I also mentioned how soils are influenced by weather and how the different elements. This diagram here is showing the different elements that can contribute to their weathering, and also can contribute to stress of soil health. So while soil is vulnerable to stresses, much like the vegetation that you see above ground. So stresses like drought and heat dome events, things like that, wind, these can all have various impacts on the amount of infiltration, the amount of evaporation, that can impact the amount of moisture that is being held in that soil. But as I had said earlier, for some types of soils, actually, well, most soils, that they have that insulating capability, that it takes a lot more to evaporate the moisture from that soil deeper down than it would if you're just looking at the soil surface. So I mentioned soil health a number of times, but what is the definition of soil health? So it's the continued capacity of the soil to function as a vital living ecosystem that sustains life. I really like this definition because, with soil health, even if there are these changes and stressors to them that threaten these systems, that we can then think about, well, if we are focusing on how to encourage and maintain soil health, then that in turn can also support the health of the systems that rely on them. So speaking of all the different other organisms that rely on soil, it's really important to take a look at the soil food web. So Soils need plants to maintain a vital living ecosystem. Organisms rely largely on carbon for their food. So without food, the soil community is less active. There's a greater carbon input through roots. Plants can help to armor the surface of the soil, protecting it from evaporation or evapotranspiration. Roots help to create pathways for water to infiltrate into the soil. And then there are these other organisms that then can take advantage of all of that. So there are nematodes and fungi and bacteria, protozoa, and they all are in the soil helping to break down some of that organic matter as they use it for their own lives. But then in turn, they are themselves food for other organisms, for different insects and mammals. And so it is, soil is alive. Whenever you're thinking about soil, it's not that you're just holding in your hand just minerals. There's every spoonful of soil has a ton of life. It's teeming with life. And so they're really benefiting from the organic matter, and they themselves are organic matter in the soil. And why do we care about this? Well, carbon. Carbon is a huge topic, as we're often thinking about how to store more carbon in the world. And so the organic matter in the soil can be in the form of roots, plant material, microbes, insects, and so on. And they are reservoirs for nutrients. And so food and energy sources for soil organisms come from the organic matter in the soil. They also provide cation exchange capacity for these soils, and they increase the water holding capacity of soils. So if there's more organic matter in a soil, it can hold on to more water, which is really important since I was talking about drought as a stress. They can also, having organic matter in the soil can decrease aluminum toxicity at certain pHs, at low pH. It can change the pH of the soil in general. And there are certain organisms that can only live in particular ranges of pH. So if there's less organic matter, then it might be in a pH range that organism cannot survive. It also improves soil structure, but that not to be confused with soil texture. So there are positive effects of the physical characteristics by the addition of organic matter. The infiltration, the drainage, the aggregation potential, so how the soil particles are able to hold together, the pore size distribution throughout the soil. As I mentioned, the water holding capacity, the erosion potential. We're going to talk a little bit more about erosion because of fire effects on erosion. The deeper water storage in the soil as well. It also encourages more diverse habitat in that soil, the diversity of all the different organisms that live in there, and just in general, increased function of that soil. So some of the positive effects on the soil chemistry of the soil by the addition of organic matter would be it buffers for a neutral pH, it increases that nutrient availability, and therefore then it increases the vegetation that can grow in there, and then that cycles back and offers there to be more organic matter inputs into the soil. So it's all pretty cyclical. And I could dive deep into the different nutrient cycles, but this is not like your high school class on nutrient cycling, so I'm not going to get deep into that, but we will continue. So soil functions rely on microbes. I mentioned microbes a bunch, referring to bacteria, fungi, protozoa. So what they do is they can increase the root surface area of a soil. So that just allows for increased exchange of those nutrients. And through that, then they can scavenge the nutrients in the water that they need. So soil organisms rely largely on carbon for their food. So without that food, the soil community is less active. And the greatest carbon input is actually through roots, plant roots. And they also, microbes are well known for making nitrogen from the atmosphere available. And they also help to make organic matter more available to plants by helping to break them down. And when there's either then those plants have access to them in the soil, or there's an actual direct connection between that microbe and the plant. They help to build soil and pore structure, and they balance pests and disease. So there's all out soil microbe territories and wars that go on that we cannot see with the naked eye. So one of my favorite categories of microbes would be ectomycorrhizal fungi, or I'll just use the acronym here, EMF, and they create symbiotic relationships with plants. They help to exchange water and nutrients for plants' sugars or carbon. And so this little inset here is actually showing the site of an ectomycorrhizal fungus covering a root tip of a tree root. And I wonder if anyone can guess. You can put in the chat. Just looking at the colors here, what do you think, what famous mushroom are these roots and ectomycorrhizae from? Oh, we got some people taking guesses. All right. Morel, Anosis, Regula, honey mushroom. We've got some great guesses. Amanita, yes. So this is actually the ectomycorrhizae of the Amanita muscaria, which is kind of neat because doesn't look a little pink. And that mushroom is known for its red and white colors. So ectomycorrhizal fungi increase growth and survival of conifer seedlings. This has been pretty well studied. And so I'm now going to transition. I'm talking so much about soils and soil microbes, but I really needed that background for all of you in order to get into how I entered into this whole topic of fire effects on soils and fire ecology of soils. Because I really was fascinated with how, okay, ectomycorrhizal fungi increase that growth and survival of these seedlings, but then what happens after a wildfire? How does fire affect the recovery and the growth of these seedlings after fire has come through? And if the mycorrhizal community is impacted, does that then mean that the ability for these seedlings to thrive, to grow and survive will be impacted as well? So that is actually what I'd asked in my research. And I'm going to only just add in little tidbits here and there about the work that I had done. So getting into fire impacts on soil, and this picture here is actually from my research. I think this would be a good time to pause to see if we have any questions.
Yeah, I was going to suggest that. So from Michael, how do composites of soil like that shown at the Black Butte in that photo get conceptualized by one of the 10 soil types? So how do you use the soil types when you talk about a composite soil that has multiple things in it?
So if you ever do get the chance to go to Soil Web, that online tool, it'll show you a percentage of the different types of soil that are part of it. It'll show you like, oh, it's 25% xeric or something, like there's all these, it gets deeper into the naming of the soils. But that's, if your question is like, how do they determine that? So when they're doing their soil surveys, they will do dig multiple soil pits and analyze and be able to identify, okay, in this percentage of this unit of land, we're seeing 25% of those pits are looking like this type of soil, this soil family. And then in this one, we see 50% of this type, if that makes any sense. Yeah.
Great. Catherine asks, does having a higher portion of organic matter in soil raise its pH?
I would say that a higher proportion resulting in higher pH. I think that depends on the type of organic matter that is being inputted into the soil. But I kind of went into that a little bit in a previous slide. Is it back here? It actually buffers for more of a neutral pH. So once again, I'll just say it goes more back to the type of organic matter, but I'll also say we can get back to you on a more in-depth answer on that.
Great. That's all for now.
Okay, hope I didn't make anyone dizzy with me clicking back and forth. Getting back to fire impacts on soil. So this picture here is actually from one of my research sites, which I'll just describe really briefly. We actually had taken temperature probes and put them in the soil at various depths and recorded the temperatures during a prescribed burn, which was more of a low intensity burn. But then we also had these areas that we're trying to mimic when there's high severity fire or when there's a large log on the ground that completely consumes. And so you can see in the middle of the picture here, there were these large logs. There's some remnants left of them, but you can see that there's a different color of the soil underneath where that material had burned. So I mentioned intensity, and I've also used the word severity. And I just want to briefly go over the difference between those terms. So intensity is more referring to the heat energy release. And often that can be referring to flame height or flame length. We have this cute diagram here of showing, okay, we got low intensity, moderate intensity, and high intensity fire. But when we're talking about soils, intensity can be described by the temperatures that were reached in the soil and the duration of heating. How long did it burn for? And so this then also relates to the different types of fires, which we talked about. I believe that was in John Punch's first webinar. Or we can have ground fire, surface fires, and crown fires. So crown fire would be an example of high intensity. Yes, in that case, it'd be high flame lengths and height, but also the temperature and the duration of heating being intense as well. So that's different from severity. Severity refers to the impact of that intensity. It's a product of the intensity. So there's a difference between severity based on tree mortality versus severity describing soil burning. And so this picture here at the top is actually, it was a severity map, fire severity map from the White River fire that was on the east side of Mount Hood in 2020. And so you could see with the red colors there, that was indicating greater than 75% tree mortality. And they create these maps using satellites and some ground truthing. Now, there's a different type of map that is produced after large wildfires, and those are called soil burn severity maps. So I want everybody to take a look at the difference between these two. And it's really interesting how in some of those places where you have a lot of tree mortality, you actually have moderate and some pockets of low severity soil burning. So it doesn't exactly match up. So high intensity can create high severity impact, but not always. And here's where I would like to ask everybody to put in the chat, why do you think that is? What would create a situation where you had a fire that had high severity impact on the trees? There was mortality of trees, but the soil did not burn as severely. Crown fire. Yes, yes, very good. So in the case of a crown fire, and in some cases, when there is, okay, there's some other examples, lack of underbrush. So sometimes it could be a fire event where it is really driven by wind. It's a really fast-moving fire. It could end up burning through the canopy of the trees and killing those trees, but actually not creating as much of an impact as you would expect to the soil. So yeah, great answers here from everybody. Various different ways that different conditions that can play a role in why some of those cases there was not as much or as high of soil burn severity. So I just want everyone to keep that in mind. When you think of a fire, you hear about a fire and it sounds extremely devastating. I truly do like to wait for them to put out these soil burn severity maps to give me hope. Because if there are pockets of soil that did not burn as severely, that's where you might have some plants that have survived, some microbes that have survived, or even if they didn't, that it's easier for seeds to come in or spores to come in and to germinate in those places, and that can help speed up the recovery process of some of these places where there was significant tree mortality. So just a little piece of hope there. Whoops, can't move my mouse. Okay, so if anyone was really curious, you could go to this link up here. It actually I created a short link, beav.es/capital G, capital C, lowercase n, needs to be case sensitive. And there you can find soil burn severity maps from the 2020 Labor Day wildfires. So pretty neat that those soil burn severity maps were put together where you can see them all in one place. So now getting deeper into how fire affects soils. This figure here, and we will be sharing the link to this study where this figure came from. This figure demonstrates the evolution of wildfire-induced processes, such as evapotranspiration and interception of precipitation, vegetation cover, root deterioration, sediment and erosion, among other things. So the burning of vegetation and organic litter can alter a variety of properties and behaviors that manifest in evolving earth surface processes. So the removal of vegetation through fire can actually enhance the infiltration because there's reduced canopy interception of rain and snow. So that sounds great, but then that also could potentially reduce the transpiration of stored groundwater. These hydrological alterations, in combination with reduction of the tree roots being there to hold the soil together, can lead to soil instability. So that can result in landslides, especially if the landscape is slower to recover, if it's slower for vegetation to come in and then grow. So the timescales of this recovery have a huge impact. So conversely, these changes in vegetation can result in the deposition of ash. And in many cases, and I'll go into more about the hydrophobic ash, but that can lead to water not being able to infiltrate into the soil, and that amplifies runoff and potential for flooding, along with increased sediment deposition and increased likelihood of debris flows. This is a big topic right now. Obviously, the LA fires are on many people's minds, and now they're getting an atmospheric river event. And so this is essentially the reason why there are evacuations going on again in some of these places, because of the concern for debris flows. Having trouble getting the next slide. So without plants being there, it creates this challenge of there being a loss of not only the above ground components that would intercept some of that that moisture, that rain, that precipitation, but really the below ground components not being able to help to aggregate the soil together. So it has an effect on erosion, an effect on the temperature, the radiation then of the soil. The soil is more open then to the sun rays being able to hit it and dry those soils out. And so that affects the moisture retention. The roots are also really important because they help to create pathways deeper into the soil that water can then flow along. And so without those roots being there, say they had burned, that then leads to more water runoff. And then, of course, if you don't have those plant roots there, and also the carbon exudates that come with them, that then you have a loss of food for those microorganisms that I described when we were looking at the soil food web. So going back to that example that I showed earlier around Black Butte outside of Sisters, Oregon, I just wanted to use that as an example, thinking about, okay, what does that landscape look like? And if a fire burned through there, which actually fire does very frequently burn through those forests there. And those types of soils there are andisols, volcanic soils. They're well drained. As I mentioned earlier, they have an incredible insulating capability, but they're also don't hold on to a lot of moisture. So these soils are actually poor conductors of heat. So as we think about the types of trees that we know that grow in those places, like ponderosa pine, which we've heard about earlier in other webinars, how they're fire adapted, that they have, thicker bark, that they often had experienced frequent fire in the past, historically. And what's really neat is that their soils are also could be seen as fire adapted in a way, because that type of soil is a poor conductor of heat. So when a fire does come through, the heat does not actually go that deep into the soil. So thinking about the different layers of the soil, the heating that's experienced stays mostly at the O horizon and only an inch or two into the A horizon. And that was something that actually, I'm going to skip that part. Something that I actually had found to be in my research. So when I had used those temperature probes in the soil, I had to keep in mind these burn temperature thresholds for different organisms. So for plant roots, that their temperature threshold, the temperature that would have to be reached for them to die is roughly 118 degrees Fahrenheit. Seeds, it's 158. Small mammals, it's just kind of strange. I don't know what study had tested at what temperature small mammals die. But bacteria, nitrogen fixing bacteria, 176 degrees Fahrenheit, and fungi, importantly, 140 degrees Fahrenheit. So these were the results from that study. And this is just the maximum soil temperature. I had other graphs on the duration of heating. But what's really neat is for these at the mineral soil surface, and the red bar here being the high burn severity treatment, that we've reached up to 1400 degrees Fahrenheit. If we think about those burn temperature thresholds, that would be killing everything. And then if you go deeper into the soil, 2 inches down, 4 inches down, you're seeing that there's a huge drop in the heat that was experienced. And then we even went 12 inches down into the soil, and that was below this legal threshold for fungi. So that was really interesting and important for us to then think about, okay, well, what fungi is living in the soil deeper down, and what is, being warmed and triggered to then grow upward into the soil and into the more shallow layers of the soil. And so also really interesting was how for the low burn severity, which is essentially what you would see with prescribed burns that occur in that region, that it was really just at the mineral soil surface where it exceeded the lethal threshold for fungi to live. Whereas just 2 inches down, it was below that threshold. So a lot of those organisms, especially the ectomycorrhizal fungi, can survive just below the soil surface in a low soil burn severity. Oh, and there it is, where most symbiotic fungi live. So if we think about this in terms of the minerals and the nutrients, the soil nutrients, these are the temperatures that nutrients are volatilized. And at the high severity burning, 1400, you see that sulfur, potassium, and importantly, nitrogen and phosphorus were volatilized at that temperature. But just 2 inches down, 4 inches, 12 inches, it was below the threshold for where nitrogen would volatilize, which is really important because, as I had said earlier, those nutrients being available to help with the soil food web. And if anyone was really curious, this is getting pretty deep in, but SOM, that is soil organic matter. So I just, for the sake of time, would say let's just focus up here at soil organic matter, and we'll look a little bit at moisture content. That interestingly, at the soil surface, that the underburn, this is what it looked like before the burn, that the soil organic matter was at this high, and then with in yellow, the low burn, the soil organic matter decreased a little bit, but then how much the soil organic matter decreased in the high severity treatment. Whereas then if you go 10 to 20 inches down, we were not seeing any of those same impacts. And in general, it would make sense. Organic matter decreases the deeper that you go into the soil anyway. So really the differences that we were seeing were just in this top region of the soil. Then looking at the moisture content, that it would make sense before any of the burns, that the percent moisture content of that soil for green here or under burn, that this was the original level, or yellow circle here, that was the low burn. the moisture content decreased a little bit, and then it decreased quite a bit for where there was the high soil burn severity treatment. And then just 10 to 20 centimeter range, there was no impact. Really interesting. I think you all understand that I'm trying to just tell the story of how most of these impacts are not as deep as you would think. And so whatever can survive at the a little bit deeper into the soil has a chance. So here it is again with the maximum soil temperatures. And now I want to talk a little bit about soil water repellent layers. But let's pause here. This might be a good time for questions and a time check.
Yeah, we do have a few questions. James has a question about those soil water repellent layers, so I'll let you talk about that first. Michael asks, he makes an observation when he fought fires, there were these smoky regions that were generally kind of the ashy pits where they've got that smoldering combustion. Is that considered an area of higher intensity because it's a longer burning fire?
Yes. Yeah. If any of you have ever walked through an area where there was a wildfire, there can be these ash pits or these, dangerous pockets where if you step into them, you could fall over or you could burn your foot if it's soon after a wildfire. So that's what Michael's referring to there. And yes, basically those ash pits are often the results of where there was either a stump or roots that used to be there that burned and were consumed, and now there is open space. So yep, you had guessed right. That is where there is higher intensity soil burning in those locations. So really the high intensity soil burning is a result of the organic matter that's in direct contact with the soil. So if you think about the roots going through the soil, if the fire is able to get to them and burn them, then you're going to experience hotter temperatures with the soil that's all around them.
So another question, this is from Leslie. How does sandy soil fare relative to heat conductivity? Is sandy soil more or less heat conductive than other types of soil?
Great question, Leslie. Do you think that there is more pore space or more air in soil that is sandy versus, let's go to the opposite end, soil that's clay? So if you think about soil that's more like clay, it has less pore space, it's closer together, and then less oxygen pockets, whereas sandy soil has more pore space, more oxygen pockets in there. And so with the greater oxygen or the greater pockets of space in that soil, there's no conductive heat, there's no direct contact that would transfer that heat. So it is a poorer conductor of heat, a sandy soil.
Yeah, so the more pore space, the less conductive. Yeah, cool,
Yes.
good. Okay, and Ethan asks, in your study on fire severity and soils, was there any looking into the bioavailable nutrients and mineral changes for that low severity fire? So how do those other things fare relative to low severity fire?
Yeah, oh, I have it later on. I bring up the same temperature thermometer
Okay,
that shows the different minerals the different soil nutrients that are volatilized. And I have mapped on there. I'll show you the low severity.
awesome. So we'll look forward to seeing that in a minute. And then
Mhm.
one last one, how is soil burn severity measured?
Yeah, so that's great. Actually, John Punches does quite a bit of that. I don't know if you want to jump in and say your definition.
Well, so there's a whole series of different characteristics in soil that we take into account when we're thinking of soil burn severity. So probably the easiest thing to do there is we can go ahead and post the really cool burn severity publication that's out there that all of us kind of go to use as a reference. And you'll see that there's a table that has several different charts in it that we use because we're looking at coloration, pore size, bulk density. There's a bunch of different stuff that goes into that. So we'll make sure we get that posted.
Yeah, that's an excellent resource we should share with everyone. Thank you. Yeah, and in that image that we saw earlier from my study, you can see that there's this red oxidized soil where there was high soil burning, high severity soil burning. And that is like one of the elements that you look for to determine if there was that level of soil burning, that
Great.
color.
That's the end of our questions for right now. I'm going to have you forward.
Okay, let's do this. Okay, water repellent layer formation. So interestingly, somewhere around the 350 to 570 temperature degrees Fahrenheit range is when water repellent layers are formed. What are water repellent layers? So essentially, we were just talking about the organic matter that collects at the surface of the soil, the leaves and needles and microbes and all those things. So those are all made up of oils, different types of oils. And so with burning, those oils will, when they reach this temperature range, the oils will separate and then they will recondense. And they will recondense deeper down in the soil. And I'll just go to the next slide so you can see what I'm talking about here. And I can come back to this if my cursor lets me. So as I was saying, that those oils recondensing deeper into the soil, you end up then getting this wettable layer of soil above that condensed layer of oils. And so then with that wettable layer, if there is a rain event, a precipitation event, it can go through and then it hits the water repellent layer, and then there's runoff. It basically, that precipitation then slides off, and what does it do? It takes with it the wettable layer of soil that's above it, above the condensed layer of oils from the organic matter. And so this is essentially what happens when you hear about erosion, landslides after fires. But really important to note that this does not happen in every single fire. This only happens if this particular range of temperatures are reached. And so think about it spatially. This graph here is looking at the depth of the soil. So in the high severity soil burning, only at the mineral soil surface did it reach that water repellent layer formation, but then it actually surpassed it. And at this point, the oils end up breaking down completely and a water repellent layer is not formed. But somewhere between 0 and 2 inches, closer to 2 inches, this water repellent layer could have formed. So we're thinking about this spatially going deeper into the soil. Now think about it also spatially across, like horizontally throughout a forest, for example. You're going to see patchiness of areas that reach this water repellent layer formation. So if it's not as severe of a if it's not as severe of a fire, then you're not going to see a water repellent layer forming everywhere. Now, if we go back to thinking about those burn severity maps, the soil burn severity maps, that can give researchers and emergency responders an idea of where maybe these water repellent layers are forming so that they can then get in there to try to reduce some of the erosion. So now I'm going to talk a little bit more about the benefits of fire on soils. So when we have situations like what we're seeing in many of our forests today, where they are not receiving the fire that they used to historically. Micah had talked about historical fire regimes. What we end up with is not only an overgrowth of some of those trees, but also a buildup of the litter and the duff in the soil that's sitting on top of the mineral soil surface. So think about if then eventually a wildfire does come through and burns a soil profile that looks like this, where there's deeper litter and duff. Because that organic matter is highly flammable, you will end up with higher temperatures reached and potentially loss of some of those nutrients and water repellent layer formation, especially since I said how water repellent layers are formed from the oils of all of those organic materials. So it is more likely to see that because a system has not experienced the frequency or the severity of fire that it did historically. Whereas in the case of, and this is not all forest types. Here, I'll use the example of a forest type that historically would burn more frequently. So those, in those cases, frequently burned forests, you would see thinner litter and duff layers above the mineral soil surface, which then when a fire would come through, you would not see as severe temperatures or duration of heating. And then important to note is that there are nutrients locked up in that deep layer of litter and duff, whereas the fire then helps to release a lot of those nutrients into the soil. Then the organic or the soil organisms have access to those nutrients when there's that frequent burning. And for each system, it's different. There can be too much burning and there could be too little burning. Just want to mention that. So getting back to this soil thermometer, showing the different nutrients that are volatilized at certain temperatures. We saw for the high severity from my research, what levels were reached. And then for the low severity treatments, that the mineral soil surface, some of the water had vaporized, but only 2 inches down, it didn't even reach a temperature where water could vaporize. And all of these nutrients were able to be maintained and not volatilized. But an interesting point to bring up here is when we're trying to utilize prescribed fire for restoration purposes, in some places, if a fire is not hot enough, it will not provide that benefit of releasing nutrients. There's other ways that if the fire is not hot enough, it could not potentially meet the objectives of that burn. But in terms of soil, that's something to think about if you really want to see that nutrient release. Whoops. Okay, this is actually going through the same exact thing I just talked about. So another interesting thing that I had noted in my results was that even with the high soil burning, there was an increase in magnesium and calcium. So those macronutrients are important, and they were bound up previously by the lack of burning. And even though we had the loss of some of these other nutrients, we did have, there's still a beneficial release of some of them. So as I wrap up about the important aspects of fire effects on soils, I really want to get back to talking about soil life, specifically soil microbes, like post-fire fungi. What's really awesome is that they will flourish. Many different species will take advantage of the release of nutrients, the ash that's there, and the dying or the dead vegetative debris, because in many cases that can be food for a food source for some of those fungal species. So that's when you start to see the decomposers and the mycorrhizal fungi, those ones that create the symbiotic relationships with different types of plants. You'll see them start to come in and create and start that recovery process. They also help just even with the soil aggregation. So I was talking about the concern after a fire of there being erosion and reduction in there could be some evaporative water loss. Just the fact that the soil fungi and their mycelia, which would be, think of them as like the roots of those fungi, growing throughout the soil, helps to hold the soil together, and also help to retain the moisture. So as soon as the soil is cool enough, that recovery process with the fungi growing throughout it begins. And so some of the common post-fire fungi that we see throughout the Cascades, you'll see some of these species. Certainly morels, or Morchella is the genus for morels. You'll see those in other parts of Oregon too. But there's also Sarcosphaera in the top here. These are really neat. They also, when I find them, sometimes I end up finding like a little frog that's living in there because it's a nice, like, moist environment where they can survive, since it's so dry out there. Different species of cup fungi. This one's Piziza. There's these cute little orange fungi, and there's Gyromitra. Many other species that grow after fire, and I bet you we're going to get some questions about that. So remember earlier I talked about, okay, well, there's in the high soil severity burning, there are warming temperatures reach deeper in the soil, even as deep as 12 inches down, but it's not enough to kill fungi. So morels, interestingly, are known to be specialists in living deeper in the soil. So in some of those cases, they are being triggered and able to then basically take advantage of the open playing field where other fungi have not been able to survive, and then they can grow upward into the soil. And I want to, just doing a little time check here, I think we have time for one more fun fire ecology and soil story, and it has to do with water repellent layers. Sure, water repellent layers are definitely a big concern, and here this diagram from Debano does a nice job of demonstrating unburned. There was this plant, there's shrub, and there's a litter layer, and then the oils, the natural oils that are in the soil, and then a fire coming through, breaking down that water repellent layer, and then that layer of oils recondensing deeper down where it's cooler in the soil. And then you end up with this this wettable layer above it. So then after that, there's been research finding that there are some species of fungi that grow deeper in the soil. And in this case, it is a truffle-like species. It's not the truffle that you think of that is, $1,000 to buy one of them. That's, at a fancy restaurant. But it's basically, it produces spores in a pocket of tissue, of material, deeper in the soil, and they rely on something to dig it up and eat it in order to spread their spores. So after the fire, these fungi are growing throughout the soil. And what's really neat is then a small mammal can, with their excellent sense of smell, can pick up on this truffle-like fungus. They dig deeper into the soil. They dig past the water repellent layer, and in order to eat that fungus. And then as a result, you have this great breaking of the water repellent layer and a catchment for where now, when there's the next rain event or other form of precipitation, that it now has a way of getting past that layer, and there being a reduced risk of erosion. So I just think that this is a really neat story of how there are organisms out there that are playing their role in the recovery that we may not be aware of. And actually, this is a picture, this is an example of that truffle-like species. Okay, so where do we go from here? All this information about how fire affects soils. What do we do about it? Well, there's definitely a lot of encouragement for protecting soils, since them being so important, being the medium that all this other life lives within and grows from. And a lot of the recommendations for protecting soils would be less disturbance of soils, making sure the soils don't get too hot, making sure that there's organic matter and litter input into those soils. Now, is that in conflict with the goals of reducing fire risk? And some of the recommendations for reducing fire risk would be creating more disturbance, whether that is through bringing fire back or reducing fuels, thinning and things like that, and breaking up fuel continuity. So I would say that there is a way that you can meet in the middle and find an overlap to make sure you're protecting soils, but also reducing fire risk. And I would say that that middle ground would be maintaining complexity. So maintaining complexity, what do I mean by this? This is actually fun because I took a lot of this inspiration from a publication, an extension publication that was about wildlife, how to create or encourage wildlife habitat, but at the same time reduce wildfire hazards and or risk. And so that publication focuses on, okay, in this size of area, maintaining snags, legacy trees, openings, patches, you can still have piles and shrubs and logs. And I thought, actually, that would be the same recommendation that I would have for protecting and encouraging soil health, while at the same time reducing fire risk. So in a sense, reducing fire risk is also going to protect these soils, because you're then reducing the amount of organic material that is in direct contact with the soil, so that you're then not having large areas of high soil burn severity. I want to convey that having some high soil burn severity is okay. And it is actually more common to see in some of the ecosystems across our state. But what we don't want to see is huge areas of high soil burn severity that are then very difficult to recover, change the soil structure, reduce the soil moisture to the point that it's harder for anything to then grow from it. So I would say maintaining the complexity of the above ground fuels will help to slow down the if fire were to if fire were to burn through here, and also then it would create more heterogeneous, more complexity in the soil burn severity that you would then see throughout this landscape. You then might see in this open patch here unburned soil or low burned soil. And then maybe in this other patch here where you might have more tree mortality, or more, maybe here where there's shrubs, it might be a little bit hotter. Here where there's a pile of debris, it might be hotter than that. But the point is that then you have these spaces within where there could be fewer loss of those soil nutrients and greater survival of some of those microbes that they can recover, or they can grow from those locations. So just want to say, supporting the thoughtful return of fire can be beneficial. to the soil, especially because we rely on fire for the release of nutrients. In some cases, there can be the question of like, oh, well, to reduce fire risk, can we just do mechanical thinning and nothing else, not use fire? And in those cases, you may not then get the benefit of what fire would do to the litter and the duff and the release of those nutrients and the triggering of some of those post-fire fungi. And so this is a very popular, widely shared image from Steve Rondo from the Klamath tribes. This is coming from the bootleg fire. And you see here, as I was saying, okay, in these places where there was only thinning and there was thinning and prescribed fire, and then there was no treatment, think about then what kind of impact not only is it having on the survival of some of these trees and understory, but also then what kind of impact it is having on these soils. So I think we can now go back into questions. How am I doing on time?
All right, we have about 10 minutes and we have a lot of questions.
Oh boy.
So any of these that you're like, that's a little complex, we'll need to come back to it. We can follow up for folks. So how do you restore soils that have become impermeable due to intense fire? So if you have hydrophobicity, is there a way to restore those soils?
Yeah, so you would want to be, another thing that I didn't mention is that there is also a time element. I said there's a spatial element to whether it's the depth of the soil or throughout the landscape, that, spatially, the creation of these hydrophobic layers. But there's also a time element, and these hydrophobic soils generally will start to dissipate on their own within 6 to 12 months. Yes, that's depending on the type of soil, but just generally that doesn't mean that they're there forever. Still, if anyone wanted to come in and do some kind of restoration, say before there was going to be a big precipitation event, I would not necessarily encourage going in and breaking up huge areas of soil because you're creating increased disturbance to those soils and then potentially creating more erosion. But there can still be measures put in place to try to reduce the erosion, like some of the baffle some areas to try to hold the soil together. Isn't that the term that I'm thinking of, baffles?
There's another name for it, but it's not coming up, but I know what you mean. The barriers,
But yeah, the barriers to
Yeah.
try to, and they'll put them in with stakes to try to.
Wattles. Somebody just typed it in.
Well,
Wattles.
thank you.
Yeah.
Wattles. What are
Yeah.
baffles?
They are baffle. That's okay.
Okay, great.
All right. So are there vegetation types or individual species that are more prone to producing hydrophobic layers when burned?
I'm trying to find that one so I could read that one. Like a type of vegetation that could
Type of
be produced.
vegetation that would be
Yeah.
more likely. So,
Okay.
for instance, would maybe waxier species be more likely to do that? Or, I mean, my understanding is that we can get hydrophobicity from almost any organic matter,
Yes.
right? Because
Yeah.
if it burns at certain temperatures, then it produces hydrocarbons that can then condense into that waxy substance. So
Yes.
I think we can get it from pretty much any organic matter. I'm not a soil scientist, so don't quote me on that. But I think they're like the waxier surfaces on some plants may be in fact more likely, but I've never come across a publication that specifically identifies that. So if somebody else here, there's obviously lots of soily sciencey people here tonight. If you've got ideas, let us know in the chat and we can, like, if there's some pubs out there, we can point people to those.
Yeah.
Let's see. So we covered that one. So one of your slides talked about nutrients being less available in organic matter that hadn't yet burned and maybe being released and be more available. So can you talk a little bit more about like why there would be stuff that would be trapped up in duff layers that wouldn't be accessible to plants and that would be released in there? Because it seems like there's all kinds of invertebrate activity and stuff going on in there, and they're getting that stuff.
They
So
are. They are. But there's other factors in here. Once again, I didn't bring up the element of time. So in some places, certainly in the region that I live in, it's dry out here. It takes longer for any of this organic matter to break down and decompose and release these nutrients, even if you have these microbes, which you actually have a lower diversity of microbes because it's drier habitat here. So still that they're doing their work, but it's slower. And here it is. This is a system that was dependent on fire, was adapted to fire, and relied on those nutrients to be released more frequently through not only the microbes and insects doing their work, but also fire. So yes, those nutrients are still being released. It's just more a matter of how quickly are they being released.
yes, that's
I don't know if there's
absolutely.
anything else you
Yeah.
wanted to add to that.
Um, Lots of questions, so we'll just move right on.
Okay.
Do you know of any attempts to introduce um, spores to post-fire areas to like improve mycorrhizal recovery?
Yeah, there are actually some studies looking into that. And at first I thought, oh, that's silly. And the reason why I thought that's silly is because people will ask, okay, well, you know what they sell in stores, the fungi amendments that you can add to your gardens, and that's supposed to help. But meanwhile, it is well researched that whatever species that you're bringing that is not native to that ecosystem will be outcompeted by the native fungi. So now some of the studies are looking into using a native fungal species that's a decomposer that won't be as likely to be outcompeted, and applying that to try to help break down some of the soil organic matter. That was only like a year or two ago that I heard about it. So I'm gonna look to see where they're at, and hopefully I can then post something on the website about it.
Here's a good one. They're all good, but this is a cool one. Do soil microbes recover more quickly in patchy, mixed severity burns?
uh gosh, I want to say in the chat, everyone say what you think. But we don't have time. Yeah, so yes. So thinking about spatial, temporal elements there, that if you have, and it's actually considered like the island effect. There are some studies looking at this, some researchers in California, where they found that if there was a greater heterogeneity of the soil burning and patchiness, that they're able to then colonize from those patches quicker if there's basically smaller groupings of areas that didn't burn as severely.
And a colleague of ours, um, Andrew Owen, his wife did a really cool study where she looked at how we could speed up recovery of plant and microbial communities in places that had been pile burned. And one of the like super logical, super easy things to do was to take a pitchfork and scatter duff and surface soil into that area. And
Yes.
there you're reintroducing the spores from right there, totally like there. So yeah, so it's really good stuff. So that's a cool
That's
thing.
it. That's a great point. I would just say that think about if it's going to be applicable
Yeah,
on a large scale.
yeah, yeah. It was like localized stuff, right?
Yeah, but
Okay,
that's good because
so
you're using native species there.
yep. Yeah, can plant roots penetrate that water repellent layer?
Yes.
This one
If
is probably beyond us, but could you comment on cryptogram activity on soils after wildfire?
maybe I'll get back to them about that. For what was first coming to mind was like soil biological crusts, but maybe that's not what they're referring to.
So David, you asked this question. It was a while back. If you're still here with us, if you can shoot us an email and give us a little more information on what you're looking for. That's beyond my knowledge of soils, so you've got me there. So send that. Let's take a quick minute here. Jacob, what's our keyword for folks that need continuing education credits?
Yeah, tonight's keyword is soils, and I'll put that in the chat as well.
Cool, thank you. All right. Now, others that are here with us, if you want to hang on, we'll continue to answer questions for a few more minutes, but we're at 7:30. If you want to bail, we get it. Thanks everybody for being here, and we'll hope you catch on the next one. But I'm going to just keep peppering away here as long as Ari will let me. So, do we have good research on fungi biodiversity that is optimal for various forest types?
Hmm. I would say it is there. We only know, this is what's estimated. We only know about 4% of the species that are even out there in the world. This soil is like, you know, almost equivalent to deep sea research. You know, what we can't see is hard to know. But what's really neat is that there have been huge advances in the last 5, 10 years in being able to, just from like small fragments of DNA, identify species all throughout the soil. You just take a sample of soil and you can get like all the different fungal species that are in there, including spores or, you know, whatever else. Um, and this research needs to continue because it has not been done for every forest type that is out there.
Great. Could you comment on the effect of freezing relative to hydrophobic soils?
I
Does it
think
break them
that
up?
the freeze thaw cycle would help to break it
Yeah.
down.
Yeah, that's one of the things that I've commonly seen as one of the mechanisms that breaks it down is that freeze thaw cycle. Let's see. Last question, what are your opinions about the use of various fuel reduction techniques such as lop and scatter, chip and mulch, air curtain burners to make biochar as opposed to potentially reburnable agents to the soil? Do you want to tackle
Guys,
that?
yeah, it's a good question. I don't have the whole answer to it, but I can tell you what I do know is that there was so much excitement about biochar, and it turns out, and this is coming from the many researchers who focus on this at OSU, that there needs to be very particular elements in place, very particular temperature conditions, and the input of the vegetative material needs to be similar in certain types in order to get to the type of char that could actually be a positive amendment to the soil and also could be stable. If anyone is thinking then about carbon, that not all char is stable carbon. It actually becomes more stable if it gets buried into the soil or waterlogged. So, you know, think about reducing oxygen available, that then the microbes come in and how quickly they break it down. But so I basically squirrel like too many ways I could go with that question. Um Lop and scatter, I mean, all of these different techniques are going to depend on the forest type, the location, the soil type, the goals, the management goals that that person would have for that particular area. Um, and lop and scatter can work as long as it's not excessive and is if it's feasible. Chipping and mulching, you don't want it to be too great of depth because apparently that increase of carbon to nitrogen ratio can then change the soil microbe community and can end up pushing it more towards bacteria over fungi or, you know, vice versa. So a lot goes into that, and maybe we'll just have to follow up on
And I
that
would
more.
just caution that from a fire behavior perspective, if you
Yes.
think about what's going to happen when fire eventually burns through a deep bed
Yeah.
of mulched material, chipped material, that's a very compacted bed.
Yeah.
And so you have a slow moving, long residence time fire, which can have significant impacts on soil just because the heat is there for so long. So it becomes a high intensity soil effect or high
Mhm.
severity soil effect, even though you may not think of it as being like a crazy fire because you may not even see flames. It just gets creep through
Yeah.
there. So I always
Yeah.
caution folks that if you're doing that, be really cautious if you're thinking about putting fire back in there post mulching, that you're going to have some implications there. So be really cautious about that. So
Especially if you're gonna leave a pile of it.
yeah, yeah. So I think, let's see. Yeah, so these are just comments made by other folks, so that's great. So thank you, everyone, and thank you, Ari, for staying on and answering a ton of really cool questions here. There's clearly lots of interest in this topic. We hope everybody will join us again in a week. Dr. Merschel is going to chat with us about really cool fire ecology stuff, some West Cascades and Coast Range. I'm super looking forward to that. So we'll see you again next week. Thanks, everybody.
Thank you, everyone.